Hello, everyone. Sorry for the little technical issues, but I think we're good to go. Okay, 8 minutes into it, but have plenty of time, hopefully, to talk about something that is close and dear to my heart, profiling, and especially now continuous profiling, which is a new thing that is gaining a lot of momentum recently. So we'll see what it is, how it's different from the traditional profiling, if you ever stumbled upon them, how it fits into what we call the three pillars of observability, or the pillars of observability: logs, traces, and metrics. Uh, Before that, a quick intro, the boring part. I am Mohammed. I work as a backend engineer for Spotify, and also a community guy. So I'm being recognized as a Java champion, Google developer expert for cloud technologies, and also a Docker captain. And I do some speaking from time to time. So the reason why I'm giving this talk is I'm a backend engineer in Spotify, and in Spotify we have this thing called on-call, and it's a standard thing within a lot of organizations, which is basically we own the services that we deploy to, and then we own also ensuring that those services perform the way they should and they stay healthier. So on-call is basically when something happens, when the service is misbehaving, we get a ping, we get paged, and then we need to react to that. And the unpleasant part is when you get paged in the middle of the night, 3, 4 a.m. in the morning, and then you just basically lost trying to understand what's happening. So the hope with basically continuous profiling and monitoring in general is trying to give us enough knowledge to react, or even better, do it more proactively, how we can avoid or minimize the outages and the issues that the teams stumble upon and the organizations go through. So that's basically why I was started getting interested into how we can improve our monitoring, how we can improve proactively getting less and less paged, and how we can make our service better, healthier, and resilient. Quick look over history and why profiling become more and more important. In the 90s, this is how the majority of the services basically looked like. It was monolith, a simple flow of communication between the client and the service, everything is packaged into a single unit of deployment, easier to scale, easier to operate, easier to understand from a mental model as well. But the problem is, if you want to scale this model, it's going to hit you hard. So in order to scale, we started to break that monolith down into multiple small components. And we started with what you call service-oriented architecture. So we decoupled the services, and we needed some means of communication between those services. So the services started to collaborate together or communicate together in order to achieve some functionality. And that functionality could be either passing data or collaborating to achieve some feature. And in order to orchestrate or coordinate that work, we needed something, a messaging queue, like enterprise service buses and MQs. But that, from our organizational perspective, turned to be too hard and too complex to operate the service buses, and we stumbled upon a lot of issues that we can probably discuss later if you're interested in. And then we moved in 2010 toward a more decentralized way of communication, with the rise of cloud native as well, into what we call microservices. And it really worked, in a sense that a lot of companies managed to run hundreds or even thousands of services in the cloud, benefiting from the microservice architecture and the cloud native technologies that powered that innovation as well. And basically, the idea is simple. We move it from centralized way of messaging into decentralized, using dump pipes and decentralized communication. And that allowed us to use even different runtime languages. So we are no longer tied to one single language for the whole organization. It allowed us basically to use the best language for the purpose that we trying to achieve, or the tool that we're trying to achieve. It helped also to move the teams from our organizational point of view into more cross-functional teams and more general purpose, and that where we started to have more feature teams that basically owns the whole life cycle of a feature and enabled smaller and more frequent deployments because the services are now smaller with a smaller runtime. However, the more instances of anything we have, the more the likelihoods it would cause issues. And it's basically, it's decentralized communication and distributed systems follows Murphy's law, which basically says anything that can go wrong will eventually go wrong. And the more instances of anything we have, the more the likelihood that some of it will break eventually. And that the problem is when we move into decentralized ways of communication, distributed systems, when something break, it can call what we call cascading failure because we rely on that software, on that application to achieve some functionality. And when it starts to break, basically bring the whole thing down. There are things that the monolithic architecture guaranteed that are no longer true when we move it to distributed systems. Services no longer start and stop in the same way, in a predictable manner. Versions might change of those services. They can have issues. We can have network issues, database issues, out of sync, and that's all of it called issues in distributed systems. And that's why they kind of hard to operate. And some examples of why distributed systems are kind of hard to operate is observing the interaction between the services. It's becoming more complex because of the way we need to orchestrate and know the traffic and the flow of what's going on and coming in. Doing traffic management and enabling things like specialized routing for A/B testing or canary deployment also become more and more critical, and how we can do that basically and incorporate experiments and those specific routing traffics without introducing issues and downtime to the users. Securing communication between those services, especially that, as I mentioned, the runtime can be different. We can use one service is using Java, another one using Ruby, another one using Rust, and then the runtime is different. So the security measures and how we can secure the communication between all the services becomes more and more challenging, and we need probably bespoke code and bespoke applications and bespoke policies for each and every runtime. And also managing timeout and communication failures. I mentioned cascading failures, and that's a well-known example of when we move to distributed systems, but also how we can manage in timeout, how we cannot stress the application in front of us when it's having a hard time and trying to basically to get some resources in order to operate. So that's also a tricky part. And then in face of those issues, whenever we have some troubles, that's industry-wise, even not IT specific, but we follow the Johari framework in order to do some risk assessments. And the Johari framework splits the risks into, or the knowledge of something into quadruplet. I'm representing only 3 here, but there are 4 basically. So we have knowledge of something. That something could be anything, but we can focus obviously on the application lifecycle of IT softwares. We have the known knowns, which are basically the things that a team knows very well about its application. And that's could be it on the metrics, on the logs, or whatever. We know that our application behave a certain ways. Some pieces are slow, some code logic is critical that we need to touch. So basically, that's the general knowledge that we are aware of for our application. And we have KPIs and specific monitoring to monitor that. We're relying on a service A that provide a third-party functionality. We know that services can be misbehaving, so we're having monitoring tools and alerts specifically for that service. The known unknowns are things that we are aware that we don't know about that system. I mentioned that we'll probably be relying on a third-party software, but that software can be misbehaving. We don't know what it's failing. One example could be if you're using a database from your cloud provider and you're relying on that. The lifecycle management of that database is basically managed by the cloud provider. If that cloud provider went down, basically that's your whole application went down, but then you still don't know when that would happen and why that would happen. And throughout this talk, And for the monitor in general, we're more trying to understand what's the why behind why things happened. And then the more critical part is the last one, which is the unknown unknowns. And those are basically the things that the team is unaware of. And those generally that's what causes production failures. Things like we made a faulty deployment and then the CPU spiked, and that caused what we call in the container system to rise to kill out because of the resources constraints in a container to be killed, or we introduced a faulty deployment that introduced a heap issue. So the Kubernetes or whatever your container orchestration tool basically kill that because it's out of memory exception. So those are the issues that happens, but we don't know why they're happening. And funnily enough, last week when I was discussing with a friend, they had an issue in their ID generation system for invoices. So there was a code that is undocumented that only generated pair numbers. And then that code was good enough for the first iteration that basically they ended up splitting up by 2, and then that generated unique IDs. The problem is when they refactored that, they noticed a 50% failure in their commands, and they spend a lot of time. So 50% of all the requests come into their service, and the purchases in their website basically just failed because of that undocumented piece of code that was looking fairly innocent. So those kind of issues that basically we're trying to understand and hopefully prevent in the future. And then our answer to the Johari framework in the IT world has been, up until recently, the 3 pillars of observability: the logs, the traces, and the metrics. A quick overview. So when it comes to the logs, they are more time-stamped records. So they give us an indication of what event happened at what time for our system. They are textualized. They can provide a lot of information about what's happened in the application, why it's happened, what's going on. And they are easier to operate, pretty cheap, easy to iterate on. And whenever we have some issue, we can just add a piece of log, and then we can basically see what's happening. And because they are timestamped, they give us a great understanding of the flow of how the code or the feature or the behavior of our application gets executed. And then most of the time, they help us to understand why things went wrong rather than just what. And that's because if they are cheap, we can follow the instructions and then try to understand why what's actually happened. And then the metrics are more numerical representation of the data of our systems, and they focus on providing the what. What is the CPU usage of my application? What is the memory consumption? What's the heap size? And all of that. So the KPI metrics could be CPU usage, memory consumption, the GVM, how many threads, and all of that. So they've mostly focused on providing numeric values that says what is actually going on in my system and trying to understand the performance of my system. And they are great in a sense. They excels in spotting issues of, okay, we see a lot of memory usage or a spike in the memory usage. So you can clearly see that in your graphs. You can clearly see that in your metrics. However, they don't provide the why. So this is happening, but we don't know why it's actually happening. And then the last one, with the rise of distributed systems, we needed a way to connect the dots and see the flow of the requests. And then that's where traces came in. And they're basically trying to help us understand the journey of the transaction, the journey of the request, and what services it went through the various components of our system. And it's particularly interesting to understand what are the bottlenecks of our application, why a specific request taking so much time, where it actually we're seeing there is a bottleneck, and how we can optimize this in order to speed up the processing of the request or the transaction. And while I was the images that I was generating, and especially the one pillar, the 3 pillars of observability, I was generating by DALI, and I was bragging how those LLMs are getting out of hand in generating images. We don't need a designer to do it, or trying to struggle with PowerPoints or slides in order to build something. And then Jonathan Ivanov, which is the lead developer for Macrometer, and it's incorporated well into the Java ecosystem world, and especially Spring, mentioned that observability should not be defined with pillars, and the amount of pillars doesn't matter. They never show the whole picture. And this is very true in a sense that pillars, or the model pillars, is an oversimplification, because no matter the number of pillars, no matter how much tools you use, if we don't basically try to correlate between all those events, we won't get the full picture and won't understand what's actually happening. And it's also, those pillars, those tools, doesn't guarantee that we have a full insight. So even we have a lot of data, those data is meaningless. So we can see the traces and understand that service A is having an issue, but if we don't correlate it with the logs and the profiles, and also with the metrics to see, okay, it's taking a lot of issues, it's because of CPU issue, it's a memory issue, it's because of something else. So without correlation between all of these, we are missing the big picture. And the 3 pillars of observability focus, as I mentioned, in fixing or understanding the 2 sides of Johari framework. So logs basically excels in understanding known knowns. We can follow them, we can understand what's actually happening. With the correlation of the metrics, logs, and traces, we can understand, oh, we have this issue. I have a memory issue. I can check the logs to see what's happening. Oh, it's in that service, it's an IO operation that is taking so long. So that's the request is so slow, and it's because there is a memory issue in there. But all of them just focus on what is happening. We can instrument the logs, obviously, in order to get more data, but that would necessitate a redeployment each and every time of your code. And then it doesn't give you basically the full picture. And then we fixed the what, but we're still missing the why, and why it's actually it's happening. So profiling was an attempt from the industry in order to understand why it's actually happening. So I have a CPU spike, and they want to understand what actually caused that spike. We can go up to the code, and that's what one of the things that profiling excels at. We can go to specific code, specific methods, specific functions, specific lines of code to understand what consumes much of my CPU, of my memory, and all of that. So profiling pretty much focus on the why, and when there is an issue, we're trying to understand why it's actually happening, and that helps to uncover a lot of unknowns. And the flow, when we incorporate profiling or profiles tools, is actually we see an issue with the metrics. So we look at our graphs and we see like there's a spikes in CPU, spikes in latency, or whatever. And then we're trying to understand why it's actually happening. And then this could be a combination of the logs and traces of 3 of them to know where actually the bottleneck is happening and where the issue is. However, we just got the what, as I mentioned, what is happening, in order to get a deep understanding and discover where actually the issue is and why it happened. Profiles excels in that. So a faulty deployment, an innocent code basically could introduce some CPU spikes, CPU issues, and then with the profiles we can understand, oh, we changed the code, that thread, that method, or that behavior, and then we are getting basically a lot of CPU usage because of it. Profiles excels in that, and to pinpoint where actually the issue happens and why. And then once we did that, the issue is no longer unknown, it becomes known to us. And then what we do through postmortems and everything, we add to the pillars of observability again to become one of the known issues that we are aware of and known knowns. And then we add specific logs, specific metrics for it in order to track it in the future and avoid such issues to happen. And then an analogy that I like to give regarding logs, metrics, and traces in comparison to profiling is, think of the three pillars of observability as the trivial health metrics. So basically, we can get with them the body temperature, the weight, the heart rate, and all of that. However, in order to gain a deep understanding of the human body, X-rays would be one of the options. And think of profiles and profiling as the X-ray of the body to help us to gain a deep understanding of how the body at all interact and spot the issues. Profiles actually try to do the same thing. It goes deep into how our system is behaving, what's consuming much of that metric, be it CPU or memory or whatever, and understand why we are seeing such issues. So examples of profiling information that we can get, starting with CPU profiling, sorry. And that's basically try to answer the question of which code, which line of code, which method, which function is using the most of my CPU. And getting that information would help to optimize the code to reduce the CPU usage. And a side benefit of that is basically making the code runs more faster, and that would hopefully reduce the latency and save the cost as well. Another example of profiling we might be interested at is workload profiling, which basically tries to answer which cause is taking the longest time to run, be it CPU or something else, or off CPU, could be memory or something, or just waiting for some resources to get unlocked. And that would help to identify latency bottlenecks, understand why my request is taking so long, even off CPU. Could be an IO, just idle waiting there for a response from a service or another component or a database or cache or whatever. Allocation profiling, that's, as the names mention, is basically trying to understand what's using most of my memory, why there are so many objects in there, what's taking or what's allocating, what's stressing my memory. And that helps also to remove unused objects, reduce the GC time, the garbage collection time, and that would basically means fewer pauses and a lot of GC work, which also would save costs and speed up the execution of your application. Lock, thread halt, different naming, stop the word, and that tries to help us understand when our function or code is getting executed, why there is stopped, why it's delayed to be executed, why stopping it is because of a lock thing or because of a GC operation that is going on, and trying to understand why our process was stopped or waited or idle in a certain period of time. And then the final one, but there are many others, is the heap profiling, and it tries to helps understand what's taking up my memory and what's inside the heap. And that helps to reduce the memory footprint of your application as well. So all of them helps to optimize the performance of your application, save the cost, and also improve the performance of it. So traditional profiling is not new, but the problem of it was was costly to operate in terms of both how we operated and how we can instrument our code in order to get the profiling information. And the biggest issue and the biggest drawback was up until recently is how much overhead it adds to the already running application, to already running environment in our code. And because of that, we limited the execution and the adoption of profiling stuff into the development environment or the test environment. So we never managed to put that into production because of the additional overhead that we have. And then that caused a lot of issues, because when we are not executed in production, it means that a lot of issues that we have in there are not captured, because production is where the fun happens. So the main problem was the overhead that they add, and that caused a lot of issues. And some profilers would need to modify the code be instrumented in order to capture some specific information, and that would require additional redeployment of our code, can't be instrumented without code modification, and that basically added some overhead in order to deploy them. They had limited visibility, again, back to because we are not running them in production. That's where the complaints come in. That's where our customer support calls us. So we have issues, but we don't see why it's actually happening. And then missing symbols in production. This thinks of symbols, and that's a term that will basically be with us for the rest of presentation, is as your phone contact list. Phone contact list. So to execute a piece of code, the CPU doesn't need to know the name of the function or what the function is. To basically need the binary code to execute that operation. However, to get that information back and to understand which method basically gets executed at what, and which line of code gets executed, we need those symbols, which is a one-to-one mapping between a piece of execution, a binary execution bit, and then which method, which line, and which function gets executed. So the symbol is basically one-to-one mapping into what is executed, the data that we got from the CPU or from the profiling, into how it's represented in our code. And there's a lot of challenges with the symbols. And one of the critical pieces of having a good profiling tool is to solve the symbol issues. But you can think of it as the contact list, a mapping between numbers and the name. If a number called you without mapping it to a name, you basically just skip it because it's likely spam, but you want to know the person without the alias that you give to that person. And then Josh Long, a great friend and a speaker in this conference as well, mentioned that production is the happiest place on earth. That's where we serve our users. That's where our code live, basically. That's where we add value. That's where we make our users happy, but also that's where the bugs happen and the issues happen. So the more we are close to the production environment, the more we can see things in the production environment, the higher is the likelihood that we can make our software better. And then continuous profiling started to get a lot of momentum recently. And it's not new. Google has been using it for quite some time. We'll see it in the next slide. But continuous profiling tries to add this continuous word or the continuous dynamic into the profiling. It means that we are continuously collecting data rather than in certain events or a specific period of time. And it's basically originated from real needs that we need to monitor our application. The tools that we have in the 3 pillars of observability offers us as, again, the what, that we're trying to understand why it's actually happening, but also has the good side effect that we can optimize our code, optimize the resources it needs, and also save the costs as well. And with the rise of cloud-native environment and cloud-native architecture, if you go to the cloud-native CNCF landscape, you can see a mayhem of tools out there. So the more tools we have, the more complex our architecture became, the mental model to understand all the components become a lot harder. And then it tries also to solve the issue that it's becoming low overhead. And we'll come back to that because that's a big claim. We're gonna go over it and try to understand it, but it makes it production friendly. So I mentioned continuous profiling is not new. It's something that Google shared in a paper that you can scan in there if you're interested in reading it. In 2010, it was basically called Google-wide profiling. And they set the base architecture that a lot of companies, a lot of solutions followed afterward. And we're going to dive into that in a minute. But it was introduced in 2010, and you can imagine that Google has been running it for quite some time before then. And then it's basically set the standard of what came afterward as the continuous profiling. But the principles are the same. So they introduced the low overhead sampling as well, which helped them to run things in production with minimal overhead. and they basically shared how they did it, how the sampling. They also introduced how they encoded the data using the pprof, which is instead of encoding the data in a text format or clear format, is basically encoded in order to optimize the storage of it. Another issue we're going to discuss as well is the storage of continuous profiling, because since we are continuously pulling the data, the amount of data we end up with is going to be huge. So there is an issue of a transfer and an issue of storage as well that we're going to discuss in a minute. And then since the paper, the continuous profiling ecosystem has evolved a lot. And in the past 5 to 6 years, a lot of tools has appeared. Google, we're obviously the one leading the wave with incorporating the profiling into their Google Cloud offering, but there are many tools that spawn up afterward, both open source and commercial, that offers more or less exactly the same feature. And then to build a profiling tool or understand how it works behind the scenes, we need basically a way to get the data. And there are two ways: either you instrument your code, or there's an agent that is trying to pull the data and get the information needed in order to understand how the code or the application is actually behaving. And then once we get that data, we send it to a program, an application that basically try to ingest that data and try to improve it, see how we can basically store it as well, and try to make sense of it. And then the core of a profiling tool is obviously the profile that basically does the magic and see how things are handled, how things are behaving, and then understand how we can manage stuff. And then I spoke about symbols. So we don't need them, but we need a way to store them in order for a later stage when we want to show the data. Symbols are really important in order to provide meaningful insights to the developers. Another important component, which is the front end and the graphs. Flame graphs are well known in that area, especially in profiling in general, especially in continuous profiling as well. So we want to combine the symbols with the profiles in order to give a big picture, but also an actionable insight to the developer in order to react in order to some event. And then last but not least, an important piece is the storage. We gathered all this information, we need to store it somewhere. And then where to store it, how to store it. It's one of the questions that whenever you are using continuous profiling is something that you need to find an answer to. How important is the information that you are getting? How much information you want to get? That's the first question. How important is that information, and how long you want to keep that information? And then that impact the size of your storage, and then storage is going to be one of the hustles and probably the big part of your bill at the end of the month. And then pretty much almost the same thing, but just more in a more visualized way. So to have the 4 pieces of continuous profiling. So we collect the data, or we profile the data, we collect it, and then we send into an analysis piece in order to understand it and provide meaningful visualization to see it. So we need a low overhead sampling profile that basically collects all the data, a way to store the data and get meaningful data out of it, and then a way to present it to the developers, to whoever might be interested in order to have actionable insights. And actionable insights is really important here. So we want to give the developers, the ops team, actionable insights with less overhead, and mainly focusing on why it's actually things are happening, and find the answers in case they need to. So we talked about we need a profiles to collect the data, and there are different techniques that we can follow in order to get that data. The simplest and most used one and well known is sampling profiling. It's basically It's also called a statistical profiler. It's basically, it collects data at different points in time. Could be 100 millisecond, 1 second, you decide. And the more frequent the sampling profiling is, the more frequent your data and the more impact you're going to have on your CPU, because it needs to capture the data, so the overhead is there. It's as I mentioned, it's pretty simple one and the most adopted one in the industry. And then we have event-based profilers. So if you're only interested in some events, like when the cache expires, when there is a lock operation, when certain events are triggered, then that's another way of collecting the data. Instrumentation profilers, those are the less used ones recently, but can be handy if we need to. It requires manual change and adding annotations or pieces of code adding lines of code into your application in order to instrument a certain behavior or a certain execution path if that's missing from your profiling tool. And then last one is threshold profilers, and it helps to capture basically outliers. Let's say you are noticing that your application timeouts for some queries. So you can collect the data or profiling information for the queries that are longer than a certain period of time. Let's imagine that, let's say a query that's taken to a database taking more than a second. You want to capture all the queries that take more than that. So you basically add a threshold that when a query takes more than that, capture all that profiles information that it has. And that obviously helps to reduce the amount of data that you send to profile for the ingestion, but also you will not have the bigger picture. But yeah, all of them works similarly. I mentioned that we want to challenge a little bit the low overhead claim. So typically, all the recent profilers, especially in the cloud native world, claim to be less than 2% generally. Some of them go up to 5%, but generally they are between 1 to 2%. The tools that I will show afterwards, Periscope, Parka, and SenseF Pixie, all claims to be less than 2% overhead, but the CPU overhead is there. But also, this is also influenced by the rate of profiling information that you get, how you get it, where basically the data is managed. Is it the symbolization? Is it managed on host or sent basically back to a centralized place to handle it? So there's a lot of elements and metrics that influence that numbers. Memory overhead, that's also an important thing to keep in mind, especially if we have the data in there and then how long we keep the data in memory before sending it to ingestion. That is within your data, within your environment, within your resources. And the longer it's on host, the more memory basically it's going to consume, and also disk. And then network overhead, because we are sending a lot of data, we're transmitting them for ingestion and profiling, all of that. So transmitting the data to a place. Sorry, I'm jet lagged. Transmitting the data to a data store where it can be analyzed. It also adds some overhead. It can impact basically the bandwidth of some important metrics for your application, and can affect that as well. So there is the low overhead compared to other ones, but the factors may change and the number may change, and something that you want to keep in mind while working with them. Some of the factors, I think I mentioned some of them previously. The sampling frequency, how often the profiler takes the snapshots of the data. A standard one is 100 millisecond. Lower than that can add more frequency, and that's more CPU overhead. Lower than that, we basically will have a broken view of what's happening because the sampling is longer. How much data you want to get and how much information you want to capture in each snapshot is also something that's gonna impact both how much disk space is gonna be used, how much network overhead also is gonna be sent as well. Symbolization strategy. Symbolization, I mentioned that is important, but to do that process of what line of code to map which execution path to what line of code, that's something that needs to be done. And that process takes some CPU of your application. So where it's done, is it on the host? And that would be basically an additional overhead to next to your application, or it has to be in a centralized way in another backend, and that's an additional because you need to send more information to get that symbolization done. So that's more IO overhead and network overhead that you add. And then agent versus agentless. We will get into the eBPF part in a second, but having an agent is something that runs within next to your application, within the CPU as well. So it adds an overhead. Agentless and eBPF, we will talk about it, but it runs, especially in Linux and Kubernetes ecosystem, it runs within the kernel. So we have minimal overhead in there compared to agents. Agent offers more flexibility. eBPF has more security concerns, especially in the enterprise world, but we will get into that in a second. And then the trade-offs is, again, how much data you want to get versus the performance impact that would bring, and also the cost of the storage. The more fine-grained insights you want to get, the bigger the data storage and the more processing time you want to have. So different strategy in there. There is not right or wrong answer. It's just like how you want to handle it and how much you are willing to invest in order to get that granular information. Some of the challenges that a lot of face in the industry, and I faced as well. Symbolization is always a challenge. Where to do it, how effective we want to do it. That's one of the things we struggle with. The tools will solve 99% of those issues, but there are still issues with it, and we will get into why in the next slide or two. Efficient data collection, also, I think we spoke about that. How frequent you want to get the data, how much data you want to get, gives you great insight, but also can be a challenge in order cost-wise. Expressive queries, we invest on all these tools. We built all these tools in order to allow the developers, allow the IT folks in order to understand why things are happening. And queries can affect basically the bill at the end of the month, because we want to optimize how queries are run similar to a database. Having indexes is always better, but also we want to give them a way to get the data, because there's a lot of data in there. We want to get the CPU, we want to give them actionable insights in order to get that information from all the data that we have. A lot of tools have built their own query language in order to simplify that process because of all the data that we have. Correlation with other signal types, that's also important. I think I mentioned in the beginning that no tool is best without, no tool gives you the full picture. You need to correlate it with other signals, other monitoring tools in order to understand what's actually happening. Widespread adoption, it's relatively new. The paper was in 2010, as I mentioned. 2020, we just started to see some tools that are getting proposed, both open source and commercial, to the whole community to use. So there's a lot of challenges in adoption and getting value out of it and see the value out of it. It needs some advocacy in there as well. And ensuring accuracy and representative sampling. We're talking about the sampling, I think, extensively. That's, yeah, you need to find that sweet spot. The more frequent, the more overhead. The less frequent, the more diluted view you would get out of your data. And then some strategies that discussing with other folks in the industry basically help general advices is how basically you can manage the volume of the data. Dynamic sampling, you basically, once when the traffic is too high, you want probably to get more frequent sampling compared to when it's the nighttime, if your service is not having like global traffic, but more of a predictable traffic, like high in the day, and then it slows down a little bit in the night. So you can have that's dynamic sampling. So instead of frequent traffic each and every time, that is simple. Basically, you can have more frequent in the day and then just span it off a little bit in the evening. How to aggregate the data? So we can have for the 1 minute, you can probably have 1 second aggregation of the data, and then more than that, you can collapse it to 1 minute. So just to reduce the data that you would need. Downsampling, things like reducing the fidelity for long-term storage, things like 1 month, you can keep up to 1 month into your active data store, and then up to 3 months in an archive, and then more than that, you probably won't look at it. So those are the questions that you'll probably need to ask and find an answer to. Data compression, how to efficiently store those data. Google, in their paper, announced an open source pprof, which is a way to compress the data and condense it to optimize, store the data in an optimized way. So you need to use similar things in order to improve the storage of your profiling data. And then target profiling. It's different than what continuous profiling is because kind of going back to the norm or the old ways of doing profiling, but it can be helpful, especially if you have some issues and you want to gain deep understanding. So if you have an issue and you know service is misbehaving, you can basically add more profiling rates or profiling information to that specific piece. But it goes against the continuous profiling that you are aiming to. But it's there if one of the patterns that some of the teams follows. Data retention policy, I think it looks briefly about that. The one that high fidelity versus short term, basically you need to collapse your data. There's less value in keeping the 100 millisecond rate for 3 months old data. You probably have to collapse it into probably a minute, 5 minutes, or an hour, and that would be fine. But keep the high fidelity for the recent data because that's what the developers and the IT folks would be interested in. Warm, the aggregated bits is the midterm, and the cold is like when the data is pretty old. How old the information is really important for you, and that would help to shrink the data storage piece as well. And then that's an internal thing that I think every organization and enterprise organization would need to go with. It's the compliance and the incidence management and all of that, how to manage it and how it can goes hand in hand with the internal policies. Cost implications, I think it's pretty much obvious, especially if you're using cloud provider. The more data you have, the more storage you use, which means the more the higher the bill that you're gonna receive at the end of the month. Things like Amazon S3, Google File Storage, and all of that. Typical storage that some of the cloud solution use, but that also means that the bill at the end of the month can be a little bit expensive. Cost optimization strategies, I mentioned some of them while talking about it. Storage tiering. So it's basically transition from how we can transition from agent profiles to optimize and our data and make it more cost effective. So the longer probably we can have it, the more infrequent it is, and also lower the time span. Efficient data formats and compression. Compression the data is really key in order to save the data and optimize the costs. I mentioned preprof multiple times, but using also compression algorithms, gzip, and all of that can help as well. Query patterns. I mentioned that most of the solutions end up building their own query language, their own DSL. just because all the optimizations that happen behind the scenes that basically empowers the people that are working with the tool without impacting the performance of the application and the profiling tool. And finally, proactive data review and pruning. Again, how long you want to keep the data, how much, what's the fidelity of the data, it's also important. And why? Why you would probably move to continuous profiling, why you would be interested in adopting it. Is there any benefit out of it? This is a good one from, I think, Grafana, because they have Periscope. So every application starts fancier, smaller, implementing the best patterns, very optimized. And then as we add more code to it, because no code stays idle, right? As we add more data, we make trade-offs, we make short-term solutions, and then the code increases and how some of the things may be not optimized. And then with continuous profiling, the hope is basically you can spot where your application is using much of its resources, be it memory, CPU, IO, and then optimize that. And that would basically means that you can lower the resources that your application needs to run, and that would mean that you would get that back in terms of the cost that you pay for your infrastructure. Another motivation is the feedback loop. And a pattern that we noticed is once you start to incorporate and introduce the continuous profiling culture, once you introduce a change, you basically you can see the changes that you introduced, how it positively or negatively affected the execution of your application. And then you can go back and optimize the code in order to make the application more resilient and more performant. So with that, it gives obviously real production insights and also data, because that's a win of using continuous profiling. It's like data-driven optimization of your application. You can see that I refactored this method. Did it make it better or did it make it worse? And how and why and all of that. And we talked about it in the beginning. It basically helps to reduce the gap between production and development environments. So if an issue happened, you are gonna see it in production, and then you can see why it's happening and take measures out of it. Some of the use cases, proactive troubleshooting. I mentioned in the beginning that we want to introduce, or one of the motivations to introduce continuous profiling is move from reacting to incidents in hopefully reducing the downtime and more catching bugs, catching issues before they happened. Once you introduce a change, you can see that the CPU has increased of your application, and then you can ask questions. Why did I do wrong? Go back to your code, try to optimize it, and then put it again without it becomes a real bottleneck, and then slow down your whole application. Better resource utilizations, we're talking about that in the cost saving, and hopefully that would help to optimize the resources that your application needs to run. Improve the application performance, I think that's something obvious. Holistic view across the entire tech stack, and that goes in coordination and correlation with the other pillars of observability. But the fact that you can go to specific line of code, specific method helps to gain a deeper understanding in correlation with other monitoring tools. And the performance regression detection, I mentioned that because once you introduce a code, you can see how bad or well it behaves once it's deployed. Okay, I still have 15 minutes. Acquiring profiles. So I mentioned there are two ways to get a profile, either agent or agentless. So this is the agent one, and it's language specific. For different languages, there are different tools, but for Java, there is the JDK flight recorder. I think that's the standard one. And there's the async profiler. The problem with the async profiler, it follows internal APIs. that it shouldn't be used, I think. So GDK Freight Recorder supported by Oracle, and it's part of the GVM. So it's better to use that one instead of async profiler. And then if you are using different languages, I'm a Java developer, so that's why I'm focusing pretty much about Java. But if you're using other languages, Go, the one of that Google is in the paper is using pprof. There are other things that you can follow for other languages. Another thing that impacts the profile information in the Java world is the safe point bias. So safe points in the Java world are a mechanism that the GVM has, and it's basically make sure that it's a snapshot within the GVM that when your code is executed, the GVM makes sure that it's a safe place, it's a safe time to run the GVM specific operations, such as garbage collection and all of that. And it does that by adding safe point information to your execution code. The problem is when we gather, we want to gather profile information, we kind of get a biased view because the green arrows are when we want to get the profile information. However, because of the safe point bias, we won't get that information. It will be delayed until we reach that safe point snapshot, the safe point pool. So that's the pool is basically stuff that or information that the GVM adds while just compiling in order to make sure, oh, this is a point where I can basically execute my own stuff. So it basically will get delayed until the safe point pool, and that will give us a biased view. It gets even worse with aligning. So the JIT compiler and the GVM does a lot of optimization. Part of that optimization is aligning, and it helps to speed up your code, speed up the execution of your code. However, since it collapses the code, so if, for example, you're having a getters method or setters methods, the GVM basically gets rid of that and then reduce it into the methods and classes that's called that getters and setters or small methods. However, the safe point bias gets even worse now, since where we wait until the end, the next safe point bias, which can be problematic. GDK Freight Recorder has a mechanism to not get into the safe point bias, but others might as well. So the async profiler, GDK Freight Recorder doesn't have an issue with that, but just something to be aware of. It doesn't only affect Java, it affects kind of all the managed runtimes. .NET is one, Python is probably another one as well. But yeah, I'm a Java developer, so Java is there. So we talked about agent profilers. Agentless profilers is getting a lot of momentum because of eBPF. So eBPF is one of the trendiest topic in the cloud native ecosystem right now because of its capabilities. And you can think of it as a virtual machine in the Linux kernel, as simple as that. And it's making the Linux kernel programmable at native execution speed, which means that we can inject code or execute code in the kernel from programs that we wrote in the user land. So we can write our programs. It's a framework, so you need to handle it in a specific way, but that's an oversimplification. But the idea is you write a program in your user land and you execute it in the kernel. How it does that? There is a specific set of steps that we need to follow. So you write your eBPF program as any program in the user land with basically two options right now that exist, either Rust or C, because that's what the kernel supports. There are other languages that are supported. I think Python and Go is also one. Java is also one. We're working on a library that does the conversion. but at the end, the execution would be C or Rust. So all the other languages basically does the translation to C or Rust languages or binary language. And then you write your program, and then you compile it into a bytecode, similar to the Java word, but that's an eBPF bytecode program. You compile it with eBPF compiler, and then you load it into a system call. So each eBPF program needs to get attached to a specific attachment point in Linux. So eBPF defines attachment points, and then you load it to the kernel. So before it gets loaded to the kernel, it goes through an important step called the verifier. And what the verifier does, it basically verifies that your code is safe to execute. It verifies things like you have first and most of all the right to execute that code. It verifies that you don't have or you don't access arbitrary memory that you shouldn't get access to. You don't expose arbitrary memory that you shouldn't access to. You don't escape and go to another CPU and all of that. So the verifier does a lot of magic. And then once the verifier gives you the thumbs up, and the verifier is, if you're writing an eBPF program, if the verifier will give you a very hard time because it's hard to get right. And then, I mean, beyond the hello world application. And then once the verifier approves it, it gets just compiled again to binary, and then it gets attached and executed into the kernel. So eBPF is event-driven. You can think of it as whenever requests came in the kernel checks, oh, is there an eBPF program that needs to handle it? And then it forwards the execution to your code, and then it continues its execution path. In a nutshell, that's eBPF. It's much more complex than what I described it in the 2 minutes, but it's really cool and a powerful technology in the cloud native ecosystem. I mentioned that eBPF need attachment points, and since it's a kernel has visibility over everything. You can attach it to up to 30 attachment points. You can attach it to the system calls, and that's basically everything, to specific functions. You can attach it to network connections, whatever in the network layers, and then some of the technologies support offloading eBPF program to hardware or to external hardware. So we can, for example, I forgot what the name is, XDP. So you can offload some of the network handling to the network card. It doesn't execute, it gets executed off CPU, not even in the kernel. So a lot of magic happening there, a lot of development happening, but all agentless, just to say, all agentless profilers are based on eBPF because it's got access to the kernel. It has visibility over everything. So it means that the information is there. We just collect it and then send it for ingestion. Safeguarding system of profilers. So eBPF, it's powerful. It's powerful because it has access to the kernel, and it has visibility over everything. It's problematic because it has access to the kernel and it has visibility over everything. So that's a sensitive. If you're uploading your eBPF program in there, be aware that you need to understand where that program came from. Because you need root access to give it access over everything. That's really problematic. But you benefit from it, but you need to be aware that you don't run arbitrary code in there, because that can bring up not only your application, but your whole infrastructure. Destabilization of the system if not implemented correctly. Mitigation strategies, I think those are well known. Principle of least privilege, don't give your application more than it needs. eBPF verifier, make sure you have the latest one. eBPF is still evolving. A lot of issues are discovered in the verifier, a lot of issues getting fixed, so keep in there. Sandboxing, it's Linux native, so namespacing helps to reduce where it gets executed and has access to. Secure communication, making sure that data that travels in your data flow is basically TLS encrypted and communicate and secured. Authentication authorization, who has access to the profile information, can be some sensitive data in there, data masking and redaction, all of that. Need to run fast because I realize I have 3 more minutes. Open source continuous profiling tools. I will run over this one very quickly. So Pixie is my favorite one because it's part of the CNCF. It's part of New Relic. So New Relic bought it and open source it. Periscope is from Grafana, follows the same Grafana stuff. It's open source. And Parka is also open source. Periscope seems to be the adopted one, well-known. Pixie is getting a lot of momentum as well. Parka is starting its ways very slowly. So Parka, it uses eBPF. Its architecture is similar to Prometheus, if you ever worked with that. It offers a CI tools, a CLI tool, and there is endpoint that you can plug your agent profiling tool into it, or your code into it, basically. And the architecture looks as the one from Google paper, as I mentioned. So you can either use the HTTP API or eBPF in order to ingest the data. It has a gRPC endpoint for that. And then it offers a UI for getting those information. Periscope from Grafana, it's more enterprise ready. It follows, it has both agent and agentless and agentless. So you can define you can use specific language agent if you want, or you can use eBPF as well to get profiles. And then because they have Grafana, so all the stuff, or the UI is basically powered by Grafana. CNCF Pixie, I mentioned, is my favorite one. It's more than a profiling tool. It's more than metric plus profiling tool, but it's benefit from that. It's getting a lot of momentum, and it's part of CNCF. It follows the same thing. It has a slightly different architecture because it provides CLI, so we can interact with the engine with the CLI as well. It provides an API client, and it's hosted within New Relic. I had a demo that I wanted to show. I'm not sure if I would have time for it, to be honest. Okay. I wanted to, okay. Mirror. Let me see my screen. Yes, you can. Okay. So I have a small Spring Boot application that in here. That's time. Very quickly, I have a Spring Boot application that is running here. So it's basically to expose a ride-sharing application. So we can book a bike or a scooter or a car. And then for each of those, I have a specific service that handles the booking. So for the bike and the car, for the bike and the scooter, you can just basically book it. For the car, we need to check the driver's availability. And the logic that handles booking the service is basically in here. So find the nearest vehicle. If it's a car, we check the driver's availability. And it's using Parka. It's using Periscope. Why Parka? Anyway, and I'm already deploying it using Docker Compose, pretty easy, and having a load generator agent that is running. You can see the logs here. It's simply a Python application that calls randomly the vehicle and the endpoint. And then this one. So you can see here that it's Periscope. Okay, maybe we can go to the root. Why it doesn't select? Anyway, yes, now it's gone. So I can select basically my rideshare application. I'm interested in the CPU, and I can define my specific tags. As you can see here, where are my tags? Where are my tags? Where are my tags? I think it's in resources. Boom, boom, boom. Where is it? Okay, if I go to the Docker Compose, Docker file, where is my Docker Compose? Can you see the resources file? No. Something is wrong here. Maybe I deleted it. I don't remember. Anyway, so somehow somewhere in the code, I think it's in the main, no? Anyway, somewhere in the code, I basically added a way to specify the region and specify which vehicle it is. So it's basically code instrumented. And then you can see that if we go to flame graph, that if, for example, if I select a bike, there is a difference between the CPU execution of the bike compared to the car, for example. So the CPU time that it's needed, it's bigger in the car. And then if I follow here, I can do the comparison one by one in the diff view. But since I'm running out of time, you can see here that I can go basically up to where it's happening. I can see here that it's, oh, there's an order service. And then there is check driver availability. There's an issue in here. And then I can basically, there's an order service does mutex lock. What is that? So I can go to the order service, check availability. I can see that it's calling mutex lock that's causing the trouble for me. If I go there, I can see at least that's happening, but I added a little bit of code in here that says, basically adds a little bit of wait time in order to track that. So having that view, that's artificial, obviously, for the purpose of the demo, but helps to understand actually what's happening and why, and take actions. So you can go basically to that level of what's happening. And then with the diff view, you can compare to when I introduce the changes compared to when not. Very quickly, I'll run through the slides. Navigating the ecosystem, language, which language you have will influence that. The deployment model, you want agent versus agent list. The overhead of the profiling tool would be one of the things that you want to pay attention to. I will skim over that. I can show you the slides afterward. Anti-patterns, set it and forget it. The TLDR of this one is and needs to be actionable. And then if you just set it and then forget about it, it's one of the monitoring tools that you don't look into it. So basically it won't add much value. So profiling is this continuous thing that they look at it daily and try to find patterns and behaviors of your application. eBPF, I mentioned, is getting a lot of momentum and is slowly becoming the unified way of collecting metadata. OpenTelemetry is entering the game. So they added as of 2020 to support event types, and it can enter the continuous profiling game as well pretty soon. Want you to end up with this. Profiling is more than just a tool. It's a capability that requires shifting mindset. So basically, set it and forget it. It's a way to continuously monitor our application, continuously improve it and update it in order to have more resilient and performance application. Thank you. I'm 5 minutes over time, so I'll have to end.